If frequency is very high, meaning that omega is very high, then this term is very large compared to the 4, then this whole term is dominated by this term. That means the whole term is dominated by omega m. That means the lymph wall is dominated by mass-like behavior of the wall. So in high frequency, lymph wall assumption is very valid. Okay? Okay, now I'm sure Yunjae, who is absent this class, would have some difficulty to understand this concept, right? Video never be same as attending the lecture, right? Of course, when I see my video, my face looks much better than what you can really see, so I prefer the video. But the way to convey the physical meaning and other details, you cannot have such kind of feeling using video. Right? Okay. So, magnitude scale, what does it physically mean? If tau is 0, what does it mean? No transmission. If tau is 1, total transmission. If tau is 100, do you think that is possible? No. If you can make that is possible, that means you will be a rich man, right? That means you certainly invented amplifier, right? So that is not possible. So I could say transmission coefficients is between 0 and 1 physically. Maybe you can prove it. Okay. What about the meaning 1 over tau square? Okay. Good example. Good example. Do we want to have tau maximized or minimized in this case? Do we want to have a window that has maximum tau or minimum tau? It depends on the way we are looking at the problem, right? So we have a source outside, and we want to design the wall so that we have no transmission. That means whatever noise is produced outside, we will certainly enjoy a very quiet environment, right? So the designer wants to make tau small or big. Small possible, right? So 1 over tau square, magnitude square, is the good measure to noise control people. Okay? And because it's a noise control problem, we'd rather use log scale. Because it is noise control problem. So, transmission loss. That is defined as 10 log 10 1 over tau magnitude. That is transmission loss. Okay, if transmission loss is 20 dB at certain frequency, and I have a noise at outside whose level, sound pressure level is 100, then how much noise I will get over here? That is simply 100 dB minus 20 dB, that is 80 dB. So that's very useful. For example, somebody say, hey, we have noise whose sound pressure level is 80 dB, and I want to make a space quieter than outside, of course, and sound pressure level has to be, for example, 50 dB. Then the input has to get a transmission loss, how much? 30 dB, right? That means I want to make a transmission loss 30 dB. Okay? So that is very useful concept for noise control people. Okay, using this, let's calculate transmission loss. And that is 10 log 10, okay, 1 plus 1 over 4, is it right? Yeah, omega m z0 scale and the scale, so this is 20, and I want to put this 4 over here, that is 2z0 and parentheses. Okay, Taeyong, is it correct? Because I saw you are seeing the text, and I want you to check whether this result is correct. Is it correct? No? No? Oh, let me check. I thought that is correct. Oh. Huh? Okay. Yeah, one scale of 1/2 is 1. Right? So now we are happy. And I am happy because that means Taeyong is not sleeping. Okay. That means this has a lot of physical interpretation, a lot of physical meaning. And now essentially, by just using this, you can behave as if you are a very good noise control engineer. Surprisingly. Okay? You can even make a company. Little bit exaggeration, I must say. Okay. If omega m divided by 2,0 is very large compared with 1, then I can write this approximately 20 log omega m over 2z0. Okay? And if I draw this result with respect to omega m 2z0 as an x-axis and transmission loss, that means